In lecture 7, we're going to start to learn basic ideas about two-dimensional NumPy arrays and files, so you can load data from a file. If you still remember what we've learned in lecture 6, and we started to use one-dimensional NumPy arrays with a plotting uh, library called matplotlib and pyplot. And we also tried one-dimensional plots using pyplot. And also we learned basic style control on your 1D plots so you can make the plots look much nicer. And also we started beginner's visualization about what kind of aspects you need to pay attention to when you make plots. In lecture 3, you will learn more about the NumPy library and by introducing the two-dimensional NumPy arrays and also basic Python syntax for loading data from files like a txt file. So recall what we learned in the last lecture for one-dimensional NumPy arrays, or sometimes we call vectors. So this is a one-dimensional NumPy array, and if you remember that, we have NumPy height equals to these numbers. And if you remember that this is the name of the array, and these are the elements, and each elements like lists, they have index, and this is the index of the NumPy array starting from 0 and to 4. So there are total 5 elements. So one-dimensional NumPy array is a basic data type of the NumPy module, which contains a series of numerical values with indices starting from 0. So unlike lists, the difference between the NumPy array and the list is that NumPy arrays can only have one data type. So also we learned index slicing of NumPy arrays, which is very similar to how you do index slicing of a list. So the syntax goes NumPy, the array name, square brackets, and the first index is inclusive and the last one is exclusive. For example, if I do np height 1, 4, so I'll get 3 elements will be 1, 2, and 3 because 4 is exclusive. So two-dimensional arrays are important and they're basically extensions of one-dimensional arrays. So in the last lecture, we basically very briefly introduced the idea of arrays, but we moved on to plotting. That's much more fun. But these are the arrays is a concept that you have to understand in computational, processes and data processes. So this is a very important concept. So an array, somewhat similar to a list, but there are important difference between an array and list. And the major difference between these two is that a list can contain all kinds of data types, and arrays they're ordered. Lists are also ordered, but arrays can only have one data type. For example, if you can define a list using the square bracket without anything inside it, and then you can append the list, use the append command by adding elements to it. But it's much more complicated to append, or we call extend, arrays in this way using a function like this, as you will see example later on. But there are other ways to do it. So why we use arrays when you can use lists? And arrays, because arrays are far more computational efficient than lists, particularly for things like math calculations. If you remember that in the previous lecture, we tried the example to calculate the BMI index. So if you have two lists and you have to write a for loop to loop over every element in your list, but if you have arrays using NumPy calculations, you can treat the lists arrays as just like a numerical value, and it does element-wise calculations, which is very, very efficient. So remember that we used the NumPy, here we know np.array function to generate one-dimensional arrays, and we can use that to generate two-dimensional arrays as well. So for example, the syntax goes import numpy as np. So if you still remember this command, import numpy and give you a nickname as np. So now I'm using the np.array function to generate a two-dimensional array with two rows, right? So the first row are these numbers, and the second row are the other numbers. And if I print the NumPy array, which is NP2D, and then you can see I'm getting a two-dimensional array, like array structure has two dimensions. One is row, one is column. So a two-dimensional array goes similar as a one-dimensional array, but it has an additional dimension. In this way is that, for example, in the one-dimensional array, everything is written in one row. But in a two-dimensional array means that besides rows, you also have columns, right? So in this way, we have this way the NumPy 2D, and we have one row and the second row and the third row, and which forms columns, and there are 5 columns, right? So if you have these structured rows and columns, and then you can introduce the idea of the row index starting from 0 to 1 to 2, and also a column index starting from 0 to 4. It has 5 rows. So you have row index and column index. So that's how you define a two-dimensional array. So in this way, the difference between one-dimensional array and two-dimensional array is that you have an additional index. Instead of only one, you have 2 indices to define the array. So remember that NumPy arrays must be single typed. So if you remember in the quiz that we had a problem question asking that when you're trying to generate a NumPy array with different data types, it's going to convert to string, everybody to string if there's a string, right? So in this case, let's try a different generating a two-dimensional NumPy array with different data types. And you can see that I have floating number and integers and also a string, right? I'm using the array function to generate a NumPy array with 3 rows and 5 columns. So if I print out the data, and you can see everything is a string, right? So the rule here is that if you're trying to generate a NumPy two-dimensional NumPy array, 1D as well, using different data types, and then if there's a string, then Python is going to convert everything to be a string. If there's a floating number, it's going to convert everything to be a floating number, right? So there are more ways to generate two-dimensional arrays, the same as the functions that we use, the zeros and ones. For example, if you do zeros 2, 3, and then that's generating a two-dimensional NumPy array with 2 rows and 3 columns filled with zeros. The same idea with ones, so this will be 4 rows and 5 columns filled with 1. So you can see these are different ways of generating two-dimensional arrays. So this is basically an illustration of axes of arrays. So for example, the two-dimensional arrays, so the first index, which is the row index, that's axis 0, and the second index is the column index going from 0 to higher number. So that's how you ordering a two-dimensional array. So there are other higher dimensional arrays in Python as well, but we're not going to be using it. But if you are interested, so this is how it's defined. So it will be 3-dimensional arrays, and it's a bit harder to visualize in mind, but just keep in mind that when it's needed, you can generate 3-dimensional arrays. So it will be 3 axes, row, column, and then the third dimension. So index slicing also works in two-dimensional arrays, because sometimes when you have a data set, which is NP2D, and I just want one value, and I have how do I access it? Or I want a subset of that value, how do I access it? Right? So in this way, index slicing goes the same idea as 1D arrays, but you have to consider 2 indices, right? In this way, it will be row indices and column indices, right? So for example, if I want to look at 1, 2, so with row 1, column 2, so how do I go? So row 1 goes with this row, which is the second row. Remember that the index is always starting from 0. And column with index 2, which will be the third one, because it's 0, 1, and 2. So this, I got the value will be 63.6 in this way. All right, so you can also do a different way, which is more like the C programming language. Here is that you can access the index with with a two square brackets. So the first row index and column index. So that will give you the same results, which is 63.6. So in this case, you can also use a index slicing to access a single row, a single column, right? So for example, if I do np2d square bracket 1, which means row with index 1, so that's the second row, and semicolon, which means that I'm going to index everything in the second row in this way, right? So row index number 1, and with everything in the column, and what I get is the second row here. So that's the result. All right, so the same idea is if I want index slicing, I want to access a single column here. I want to column index with index number 2. So what happens here is that I'm access everything in the column number 2. So I get one column of the data, and I print the data. This is what I get, which is exactly this column, right? Remember that it's starting from 0, so 2 is the third column. All right, so think about this. What if I do 2, 1 to 4, right? So that will give you a subset of the data in row index with index 2, right? So in two-dimensional NumPy arrays, and there are useful attributes and methods that you can use to operate on the arrays or get the information of the array. So attributes are basically information of the array. For example, there are 3 important attributes that you can access when you define a NumPy array. For example, which the first one's ndim, which tells you the dimension of your array. For example, I define a NumPy array as a equals to np.array with a two-dimensional array down here. So that will be 3 rows and 3 columns. So I will do the print the dimension of a. Dimensions of a's are a.dim. So if you do this, remember that use the dot operation. So a.dim, which means I'm asking Python to give me the dimension of the array, right? So now it's 2 here. So the same as the shape function. So the shape, it's not a function, it's an attribute. So the shape tells you how many elements are in each dimension, right? For example, if I do a.shape, and it's going to return a tuple which has 2 numbers in it. In this case, will be 2 and 3 because it's a 2-dimensional array with 2 rows and 3 columns as it's defined. All right, the last one will be size. So size, the attribute size tells you how many elements in total is included in the array. So in this case, a.size in this one will be 6, right? 1, 2, 3, 4, 5, 6, because that's 2 rows, 3 columns, so that's 6 elements, right? So remember that's because these are attributes, so there's no parenthesis needed when accessing those arrays because these are not functions, these are just attributes. All right, so array functions, as you have learned before, for example, like sort and clear and all these functions. And also for two-dimensional arrays, there are some interesting functions that might be useful. And for example, the flatten method, these are functions or methods. There's methods of basic functions. So the flatten method basically claps multi-dimensional arrays to 1D arrays. For example, if we have a dimension array A equals to np.array with 3 rows and 3 columns, that's a 3 by 3 array. And if I do b equals to a dot flatten, remember there's to have parentheses because flatten is a function, not an attribute. So if I print out a and then b, and you can see that a is a 2-dimensional array with 3 rows and 3 columns as defined. But b, because b equals to a dot flatten, parentheses, means that I'm converting this 2-dimensional array to 1D array by just putting all the data into one single row in this case. All right. So also you can do the reshape method, and which changes the shape of your array. So you change the row and column in an array. And this is used a lot in data processing when you're producing, converting 1D array to 2D array or vice versa. but we're probably not going to use too much in this class, but you just need to get an idea that you have a function like this to use. So for example, if I define a 2D array with 2 rows, 3 columns, so that's 6 elements in total. So if B equals to A dot reshape 3, 2, which means I'm going to change A to be also a 2-dimensional array, but with 3 rows and 2 columns, instead of 2 rows and 3 columns. Right, so then I print out A and B with a dashed line as a separator. So you can see that when we print out the results, A is a 2-dimensional array with 2 rows, 3 columns as defined, but B now is shifted, right? In this case, B has 3 rows but 2 columns, and ordered in this way as the same how you go to one to the first one to the last one. There are also append methods by adding new elements to arrays, which works in a very bizarre way. So just get an idea of how these functions have, but we're probably not going to use this because the problem with this append function in the NumPy array is that you try to append one row into the existing array with 3 rows here, but then it's got flattened to a 1-dimensional array. And then if you want to put it back, and you have to use the reshape function, right? So that works in a very weird way. So we're not going to pay too much attention to that one. So also remember that in the 1-dimensional Python or NumPy array, we have functions to convert lists to a NumPy array just using the array function, right? So you can also do the other way around, which you convert a NumPy array to a list. For example, the function is called toList parentheses because this is a function, right? So if we use the A array defined previously, and then we do a new function, a new variable called L equals to A dot toList. This means that I'm gonna first convert everything in A to be a list and then give the values to L, right? So in this way, if I print out A, it's the 2-dimensional array with 3 rows and 3 columns. And then if I print the L, which is A dot toList, so now everything's converted to a list, and now I have a list which has 3 lists inside it. And if you print out the type here using the type function, so original type A, original A is a NumPy n-dimensional array, which is 2-dimensional array. And if I print out the type of L, which is a list, right? So remember that list can also have lists inside. All right, so if you want to do the other way around, and you can just do np.array, use the array function to convert a list to an array. So if you do that and you come back to a 2-dimensional array from the list L to a 2-dimensional array in this case. So besides generating 2-dimensional NumPy arrays using the array function, and we can also load 2-dimensional arrays from files, which is a very useful and very important skill for data analysis because most of the data sets are stored in computer files such as a TXT file or an Excel file. So to start with, first we're going to learn some basic ideas about how to read in data or load data into the Python using the NumPy functions. For example, here is a data file called temperature.txt. Let's take a look at what that data file look like. All right, so this is the screen on my computer, and you can see that this is a data file. So the temperature.txt is a file name, right? So the file has 139 rows and 3 columns. So 3 columns, 139 rows. The first column gives the year of the measurement, and the second column gives the measured annual anomaly temperature in Celsius. And the third column is the long-term trend by removing short-term variations. And later on, we will learn how to generate that using a special library. Right, this is called time series analysis. All right, so the first thing to do is that I have this data file. So how do I convert this data file to be a 2-dimensional NumPy array so we can make plots and make analysis? Right, so to do this, and Python provides a very simple function here. So first, take a look at it. So import numpy as np, and also import matplotlib.pyplot as plt. So that's my plotting library. So the function I'm using here is called load.txt. So the input to the function is the file name here. So this might be look slightly, not familiar to you, but to me is that so datasets is a folder in my computer, and that has a function named temperature.txt. So when you try to download the temperature.txt function in the same directory as your working IPython notebook file, no, not IPython, Jupyter notebook file, and you can just ignore the data sets here just using temperature.txt. So Python knows that I'm going down to the same directory as the Jupyter notebook file to find this file. All right, so when I after loading this file, I'm giving the value to a variable called temp anom, which is temperature anomaly, right? So this descriptive name. So now I'm going to use the print function to first print out the type of temp anom, and also I'm printing out the value of temp anom. So see what the results look like, right? So first I got the type of temp anom, which tells me that it's a numpy n-dimensional array, which is two-dimensional array. And if I just print temp anom, and you get that I got a two-dimensional array printed out with 139 rows and 3 columns in this way. All right, so in this case, temp anom is a two-dimensional numpy array, and using the load txt function, and it has 139 rows and 3 columns. And then the first column, if we do temp using the column index 0, and I'll get all the years. And if I do the column index 1, I get all the annual anomaly temperature. And if I do 2, and then I got all the long-term trend in the by removing the short-term variations. Now, so all these 3 index slicing gives you the one-dimensional array. So remember that you can use that to make plots, and we will show that later. All right, so remember that you can get attributes of a two-dimensional array. For example, if I'm printing out the data type is type temp anom, and then it gives you that the data type is numpy.n-dimensional array. And then the shape of the array, I'm using the shape attributes and also temp anom.size and temp anom.ndim. And you can see it's telling you that the shape of the array is 139 and 3. And the size of the array, which tells you how many elements in total in the array, that's basically 139 times 3, which is 417. And also the last one, the ndim, tells you that the dimension of the array is 2. It's a two-dimensional array. Now when we load the two-dimensional array, we can make plots using the data from the two-dimensional array based on the plot function we used for 1D arrays, right? So let's take a look at this code. First, we import the NumPy library and the PLT library, and then we load the text file, which contains the data, which is temperature.txt down here, and load there. And now we give the two-dimensional numpy array as a name as temp anom. Right? Remember that temp anom now is a 2D array with 139 rows and 3 columns. Right. So first, let's do array index slicing. Right. So year equals to temp anom column 0, which means I'm taking the column index of 0, which is the first column data, and give that 1D array to be a year. So remember that with this syntax, when you do the array slicing like this, I'm only accessing one column, right? So one column extracted from a two-dimensional array, which is a 1D array, right? So the same idea, I'm giving the second column as the annual temperature anomaly to a new variable called anomaly. And also I give a long-term variation to low-res here. And also you can do subtraction by subtracting low-res, which is the long-term variation from the annual anomaly, which is the year-to-year variation. Right? Remember that why we can do that? Because both of them are NumPy arrays. If they're lists, and you can't do that. Right, so now let's generate a plot giving a figure size down here, and I do plot 1, and here I plot year anomaly as a function of a year. I'm using a marker, circular markers, and I'm label this line as annual mean. And then I'm also plotting a second data set which is the long-term trend as a function of a year. I'm using red line with the label called running mean. And also I'm label my axes as year. I'm also label my vertical axis as degrees. And this is just a LaTeX syntax for subscripts. And also I'm giving them my function my plot a title called global land ocean temperature index, right? So I plot on the legend, and don't forget to do plt.show, and this is plot I get, right? So you can see that the annual temperature is done by circles using markers, and also the running mean are done by a red curve down here. So you can see that these are annual variations. This is the long-term trend of the temperature anomaly. Right, so later on in the lecture for time series analysis, and we will learn how to generate this red curve based on these blue dots. All right, so you can also make plots with 2 panels, and let's take a look at this. So that's the same code, and by doing this, I'm adding a subplot, which is 1 row, 2 columns, and this is one subplot 1 to 1, which is the first panel, and we've explained this in the previous slide, and subplot 1 to 2, which is the second panel down here, right? So now here we are plotting using a different style down here. I'm plotting plot the long-term trend, which is loris, as a function of year, and using a blue line, solid line, and labeling running mean. And the next one, remember residual. So what is residual? Residual is actually the annual anomaly by removing the long-term trend. So that's the year-to-year variations of the temperature anomaly. And you can see that I'm plotting this using a red solid line and label it as residual. And I'm labeling my axis and give a title here. So if you do this, and you can see I'm generating a second plot, which showing the long-term trend and then the year-to-year variation. So these two added together are basically the raw data, which is the temperature anomaly. Right. So this kind of data set processing we will learn later is called time series analysis, and this is called time series decomposition. All right. So now you can see that in the data file, we have the temperature data file. We put all the temperature. If you use the plot function, and we keep adding plotting stuff to the one plot, and everyone's using the same axis or the same scales, right? But it's actually much better if you can use different scales for different data sets. So for example, this is how we do it. And this code is in the Jupyter notebook for the lecture, and you can just use this and use this syntax, and by replacing these variables with your own variables and to make your own plots. Right, so the key here is that you use the subplots function to generate 2 axes. One is fig, one is x. So axis.1, so it's axis1 dot plot, and we will do a plot results as a function of a year, and using a blue solid line, and we do label and everything, and then we do the ticks, and with all these labels match the line color. So the tick will be in the y direction, and we will use the color as B. So if you do look at this, so ax1.plot generating all these blue line with the temperature variations with these blue labels in the y-axis. All right, so to put on another plot with a different axis, because the reason why I want to do that is because look at the range. So the temperature anomaly going from 1880 to 2020 here varies about 1.5 degrees. But the year-to-year variation, which is the residual here, varies only like 0.1 degrees, right? So if you put them together with each other, and you can see that, this variation is much smaller to visualize compared to the long-term trend, right? So the idea is that we want to show the red plot with a different scale. So you can put two of them on the same plot by using different scales to visualize them, right? So in this case, the trick is to use two different x's. So here ax2 is based on ax1 dot twin x, which means that they will share the same x-axis, but they will use different y-axis in this case, right? So now I do plot the residual, which is results the anomaly minus ROS as a function of year and using a red line, and these are all the style controls. And also I'll set label and set the ticker color as red. So this line of code sets everything to be red down here. So the other one is that now when I decide for this axis, if I don't have this line of code, which is the set ylim, and I'll be using exactly the same ylim as here. So now I'm using set ylim here to 0.3 to minus 0.3 to 0.3. So you can see that the axis for the second axis is minus 0.3 to 0.3, right? So fig tight layouts and plt.show, and these are functions just tell Python. These are functions from Python to tell me to show the function in here, show the plots here. So using this code, and you can see now I'm generating a plot with two data sets sharing the same x-axis, which is year, by using different y-axis. Right? So this is a nice example that you can use in your future homework or practice to generating plots like this. So you can just copy this part of the code and replace these plotting variables and control, choices, variables, limits as your own, which works for your own plot. All right, so there's another handy Python NumPy function for loading data from txt file. It's called the gen from txt. So for example, we have the following data file from Hurricane Maria with track data. So the data looks like this on my computer. So if you look at this, it's very complicated. So this is actually the track data of the Hurricane Maria happened in 2017, and which is a super typhoon in this way. So it's a hurricane. So that's on the other side. And then you can see that there are lots of data sites, data points included. For example, like this looks like the date. This looks like the time. And these are longitude, latitude, and speeds and everything, and lots of data sets, right? So this is a very complicated data type. And with the file name is called maria underscore data.txt with 60 rows and 18 columns. And the first two gives a UT, like the year and the time, and the rest are longitude, latitude, and then the wind speed, and later on, right? So the difference between this one and the temperature.txt there is that this one is slightly more complicated. It has all the data points are separated by a comma here, right? Right. So if we do that, and how do we do that? So the idea about loading this file, we use a function load this file, and you need to tell Python how to differentiate different data points, right? So now the function we're using here is called gen from txt function, right? So the difference, slightly more complicated compared to load txt, is that the inputs, now we have one data is a file name. First input is file name. Second input is called delimiter, which tells you what's separating a data point, right? So now here, remember that in the Maria data.txt file, the separators are comma, right? So if we do delimiter equals to comma, which is a string down here, and then Python knows that it's gonna go down to this file to get this data, and generating a two-dimensional array separated by the data points are separated by comma here, right? So now Maria is a two-dimensional array, and which contains all the data from the Hurricane Maria. And we know that the fourth column The fifth column is the wind speed. So how do we access the fifth column? Remember that index slicing? So we do speed, which is a new variable, equals to Maria column 4, which means the fifth column. So that's the speed. So I'm accessing this wind speed from the Maria array and give it to a new variable called speed. Now I'm using plt.plot speed, and I'll tell me it's miles per hour. So now you can see that this is basically the wind speed of Hurricane Maria, right? So this way it's the same idea. I'm accessing one column from the two-dimensional NumPy array, and then I'm plotting it using the plot function, right? But this plot is not so great because there's no x-axis, and we will learn more later on. All right, so this is lecture 7, and let's go to the in-class practice and make some plots.